Yeah, I don't want to forget later. And I will share screen with you. Okay, so you have seen this before. Um, sure. Just 1 second. I don't know why it's not working. Yeah, just few more people to admit. Okay, right. So can everybody see this? Can everybody see the slides?
Yes,
Yes,
ma'am.
ma'am.
Okay, good. So if you remember, yeah, this unit is of course um, linked with formalism. And just to jog your memory once again, you're probably getting pretty bored of me saying this over and over again. Formalism essentially tells you the basic principles on which quantum theory is based. Okay. It also develops all the mathematics that is required to do calculations in quantum mechanics. So, what you're going to be learning over here are essentially principles, and you're also going to learn techniques of doing the calculation, right? So we know this. Let's go on to the next. And then we learned a whole bunch of postulates. Okay, I went over this on Thursday, so I'm going to go over this very fast. The first postulate essentially tells you that if you have an ensemble of physical systems, what does that mean? It means you define a system. It could be an electron in a box, it can be multiple particles in a box, it could be a simple harmonic oscillator, okay, any of these. And you think about every possible configuration of that, okay, energy wise, position wise, you think about every possible configuration, and that entire thing forms an ensemble of physical systems. So if you take an electron in a box, that electron being in any position, any energy inside the box, that will make the ensemble for that particular physical system. Now to that you can associate a wave function or a state function. We learned certain things about the wave function or state function. We learned that it is a mathematical function, and in general it can be complex in nature. Okay, so that complex by I mean the number, not that it's complicated. Okay, you can also multiply it by an arbitrary number and the meaning of that will not change. Does it have a physical meaning per se? No, but it contains all the information about the system. And okay, so we'll go back to that later. uh, Also, the function is single valued, but this is in general a definition of any function. Okay, for one specific set of variables that you have, the function will have only one value. Okay, only then it's a function. So this wave function is also like that. It is continuous, and its first derivative is also continuous. The function is square integrable, which means that this quantity that we see over here, it is a finite quantity. And you know that I've told you this, that this means that you can also normalize it. Then why does the normalization become important? Please remember that is because we interpret this particular quantity which is being integrated, this psi star psi or mod psi square, as the probability of finding the system at those coordinates, right? And thereby, if you can normalize it, which means that you do manipulations with this using this particular property. Just 1 second, I have to admit somebody else here. By using this particular property, that when you multiply it with an arbitrary number, it does not change, the physical meaning does not change. And what we then do is that we made this integration, this finite quantity here, we make it 1, which means the probability of finding it at any one possible coordinate, any coordinate, okay, is always 1. That means the system exists. Okay, so we make it 1, and then this interpretation of this mod psi square as a probability becomes easy for us. All right, and then what did I tell you? The set of all square integrable functions form something which we call as the Hilbert space. And let's not worry too much, but you should be familiar with the term Hilbert space. Then we went on. Okay, I'm having some trouble changing my slide. Okay, I'm going to stop share and share again. This is very annoying, but it happens. I am audible, right? All of you are able to hear me? Because if you aren't, please tell me immediately.
Yes,
Okay, thank you. All right. Okay, somebody else has entered the. Let me go to slideshow. Okay, resume slideshow. Yeah. So okay, now it's changing. So then the second postulate we encountered was a superposition principle. And what did I tell you about the superposition? Remember, now we can essentially call these things as linear combinations. Okay, so if you can imagine that these are all the psi 1, psi 2, psi 3, psi 4, psi n, they are all members of an ensemble. Then, if you take a combination like this, which is called a linear combination, you can do it for two of them, you can do it for n of them. Remember that the final product, final answer which you get, the final sum that you get, which is a psi, that psi is also a member of the ensemble. And then, if you remember, we essentially came up with the idea of an inner product or a scalar product, which is defined like this. If you take two wave functions psi and phi, then you define the inner product like this. And this tells you the extent of overlap, right? So if the answer for this is zero, it means that they do not have the same information at all. They do not share any information at all. On the other hand, if it's a finite number, then it could be that you will be able to figure out that there is some amount of information that they share between each other. And if it is both of them are normalized and you find that this number is equal to 1, then you will realize that they are completely overlapping. They are actually the one and the same wave function. Okay, I will go on to the next what do you call postulate, and this is where we brought in the concept of a what is it an operator, right? And why do we need operators? As I told you, we have a wave function, and the wave function has information about the system, but we need to know that information, right? I mean, it's very nice, the information is all there, but we need to know the information, and to do that we need to do certain mathematical operations on this function which we call as the wave function. And that mathematical operations we call as an operator. So obviously, depending on the kind of information we want, we are going to have different operators. If we want to know about the energy, we'll have to use the energy operator. If we want to know about the position, we'll have to use the position operator. If we want to know about the momentum, we'll have to use the momentum operator. Okay. So what we said over here is that with every dynamical variable, which means every variable which is changing with time, we have an operator that is associated. And additionally, there is this qualifier over here. We call it a linear operator. So what is a linear operator? Please, please, please remember this definition very clearly, that if you have A operating on C1 psi 1 plus C2 psi 2, you will get C1 A psi 1 plus C2 A psi 2. Okay. Then I got you to a very, very important equation, which we called as the eigenvalue equation. And what was this eigenvalue equation? Basically, when the operator operated on a wave function, it gave you a scalar number times that same wave function. Okay. So this A is a scalar constant. And then we call, sorry about that. Oh, yeah. Then please remember, we call the psi as the eigenfunction of A and A as the eigenvalue of A. All right. And why is this important? Because this now can serve as a measurement. Okay. So when you have the system in an eigenstate of the operator, you can say this is a measurement of that dynamical variable for which A is the operator. So for instance, if A was the operator for energy and we have an eigenstate of the energy, then we basically are going to get this value A, which we can say is the energy of the system when it is in this eigenstate. Okay, so it can serve as a measure. Of course, then it becomes very important. Somebody is not on mute. Okay, I'm going to put them on mute. I'm sorry. Yeah. Um, there is another important thing that is required now, that if this is going to be a measurement of a physical quantity, it is extremely important for us that it is real, because we do not know how to interpret imaginary or complex measurements, right, of physical quantities like energy, position, momentum, right? So thereby so that's what I've written over here, the postulate. The only result of a precise measurement of a dynamical variable is one of the eigenvalues of the linear operator associated with the variable. I don't know how I keep doing that. Yeah. All right. So and to kind of ensure that we can really interpret it as the, just one second, I think I will use my annotate button, because otherwise I keep changing the slide, which is not good, very confusing for me also. All right. So the point is that if we really want to use it as a precise measurement, then we need certain additional qualifiers on the operator. And what was that? We basically need a Hermitian operator. And essentially, this is how we define an Hermitian operator. Okay. So any operator which can satisfy this relation is called a Hermitian operator. And what we did over the last few classes was to learn essentially what are the properties of a Hermitian operator. And what we wanted, you remember, we wanted the eigenvalues to be real. So we found that for an Hermitian operator, the eigenvalues are always real. Not only that, we went ahead and found something interesting, that the eigenfunctions of the Hermitian operator form an orthonormal set. And this is how we define, just one second. This is how we define, just give me a moment, please. This is how we define essentially a, an orthonormal set. Okay. Basically, you have an operator A, and these are its set of its eigenfunctions. So remember, I can take several values. It can take, say, from 1, if there are n eigenfunctions. It can be from, let us say, I equal to 1 all the way to n. It could be even continuous. Okay, you don't have to have discrete eigenfunctions. You could have continuous functions. All right. And when it satisfies this particular condition, that is the inner product between psi I psi j is equal to delta ij. Remember what I call this? I call this the Kronecker delta function. And this will be equal to 0 when I is not equal to j, and equal to 1 when I is equal to j. And then we say it is an orthonormal set. All right. And last time, I think this is what we did in the last class. So if you have any doubts, please come up with it now. All right. And what did we talk about in the last class? Essentially, first of all, we came up with this idea that, okay, when the wave function is in an eigenstate of a particular operator, then yes, we will be able to get the eigenvalue equation, and we will be able to get a measurement of that dynamical variable. However, if it is not in the eigenstate, what do we do? And that is when you come up with the definition of this particular thing, which is called as the expectation value or the average value. And how is it defined? It is defined basically like this, that on the top you have the inner product between psi and a operating on psi, and it is divided by the inner product of psi with itself. You know, this quantity, of course, will be equal to 1 if psi is normalized, right? Then what did we do? We basically said that, hey, listen, if you have now a set of eigenfunctions, okay, I'm giving it a slightly different name. I'm calling them ui, not psi I, but it doesn't matter, okay? So if we had a set of eigenfunctions which belong to an operator A, and then we know, of course, that they form an orthonormal set. Now, this is something I forgot to say to you last time. If this set, okay, what do I mean by this set? This set of orthonormal wave functions, which are eigenfunctions of A, if they can, so let me just say it correctly. uh, you have a vector space, okay? So what do I mean by this vector space? These are essentially all the wave function that describe the ensemble. All right. So you have a physical system, you have every possible configuration of the physical system, you have all those particular functions which are associated with those configurations, and they form an ensemble, right? and that set of functions you're calling as a vector space. Now, if each and every psi which belongs to this vector space, if you can write them as a linear combination of these functions, okay, what are these functions again? These are the eigenfunctions of an operator A. Remember that that operator is a Hermitian operator, okay? That's why you know that these form an orthonormal set, all right? So if you can pick up any wave function from this vector space, and if you can write it as a linear combination of these ui's, then what do you say? You say that, look, this set ui, okay, this set over here, this ui, it spans the vector space. It spans the vector space. What does that mean? It means that each and every wave function that you have in that vector space can be written as a linear combination of these eigenfunctions. Now, any doubts in this, please? Because I didn't explain this last time, so which is why I'm taking a little time to do this. Does anybody have any doubt in this? Have you understood this idea? Okay, I'm going to stop the share and ask you, have you understood this idea? Are you all asleep? Hello?
Yes, ma'am.
You've understood. So I will just take a little bit of, so let me just do one thing. I will just explain it on the whiteboard once, okay? So let me just do this. So basically the idea is this. You have a physical system, right? Is this visible to all of you?
Yes, ma'am.
You have a physical system. So what do I mean by that? That maybe it's an electron in a box, maybe it's multiple particles in a box, maybe it's a simple harmonic oscillator, maybe it's a hydrogen atom, maybe it is a rubidium atom. Okay, we don't we are not specifying it. All right, so it may be a physical system. So every possible configuration, let's imagine, of this particular physical system. All right, we are imagining every possible configuration. Now, every possible configuration, please remember, will have some function. Okay, so these we call what? We call them wave functions. They are special functions, right? We call these wave functions. All right, so these are going to define each of these configurations, and together they will form an ensemble, right? And this is what these set of functions, okay, which are defining this ensemble, we are going to call, they constitute what we call as the vector space. All right, so this is your vector space. So now let's talk about something else. We have A, which is a Hermitian operator. And what did we learn last few classes? We learned that this Hermitian operator, it will have a set of eigenfunctions ui. So these are the eigenfunctions of A, right? These are the eigenfunctions of A, all right? And what we will say is that if you pick up a psi that belongs to F, all right, then suppose you can write this psi as equal to summation over I, some Ci, which is a scalar constant, multiplied by ui, okay? And you can do this for all the psis that belong to F. Then what do you say? You say that this set ui spans F. Okay, you will say ui spans F. This is what I was trying to tell you. Okay, is this clear to everybody what I'm trying to tell you? What do I mean by spanning? Okay, so I think you have already done vector spaces. You know the idea of a basis, right? Yeah, you probably know the idea of a basis. So essentially we are trying to do this. We are talking about a set of eigenfunctions of a Hermitian operator acting like a basis for this vector space, which actually describes the ensemble of a physical system. Yeah, Sumaya, I think I have seen you raise your hand. Please ask. Sumaya, you have a raised hand. Do you have a question? Have I lost you guys or are you still there? Oh, it's a mistake. Okay, fine. No issues, no issues. Fine. So let me just go back to my slide again. All right. So let me go to the. Yeah. So now, so I hope everybody has understood this whole idea that you have a set of eigenfunctions of a Hermitian operator and you have this vector space. Of course, this set of eigenfunctions will themselves be members of the vector space. Okay, remember that. It will be members of the vector space. So like for instance, if you take every position vector, right? That forms a vector space, right? Every position vector forms a vector space. What is the basis of that vector space? The unit vectors in the xyz direction, for example, that is that I, j, and k. I, j, and k are themselves position vectors. You know that, right? And you can write every position vector in terms of a linear combination of the I, j, and k. Then you will say I, j, k, the set of these three vectors spans three-dimensional space. It spans the entire set of position vector. Okay. Similarly, over here, you will say that if I have a Hermitian operator, the Hermitian operator, of course, has a set of eigenfunctions, which I know forms an orthonormal set. We have proved it. If these orthonormal vectors, okay, this set of orthonormal wave functions are such that if I pick any member from the vector space, I can write them as a linear combination of these eigenfunctions. Then I will say that this set Ui spans the vector space F. Okay. Then what did we do last time? Last time we proved for ourselves that this expansion that we are talking about, what do I mean by expansion? Instead of writing it as psi, I'm writing it as a summation over I, ci, ui. So obviously it's an expansion, right? You can just have a position vector or you can write it in terms of a linear combination of I, j, and k, right? So that is like an expansion. So this expansion, please remember, is unique. How would you write a position vector in terms of just, by itself? You'll write it as magnitude into e to the power of I theta, right? That's a polar representation. Or you can write it as an expansion of some number multiplying unit vector I plus some number multiplying unit vector j plus some number multiplying unit vector k. So that's an expansion, right? So similarly, I can have the wave function over here and I can expand it in terms of these eigenfunctions. Now, what we proved last time is that this expansion is a unique expansion. What do I mean by a unique expansion? That suppose I write psi is equal to summation over ci ui, and I also can write psi is equal to summation over di ui. Then automatically every di is equal to ci. I can prove it. Okay, so which means there is only one way of writing this expansion. Any doubts? Any doubts? So we did this proof last time. Did everybody understand it? Last time we kind of, I did this proof in detail. Has everybody understood it? Yes or no?
Yes, ma'am.
Huh? Everybody's good with it. Because if
Yes,
you
ma'am.
have any doubts, then we will try and, we will do it again. Okay, so now let's move on. All right, so let me just go back here. Okay, so I think I finished that. Now let's look at what I have written over here. All right, so now let us think about the situation that we have a set of eigenfunctions of a Hermitian operator When we pick up any Hermitian operator, you know that it will form an orthonormal set. That there is no doubt. But what we do not know is that if we have the entire vector space, will this orthonormal set span the entire vector space or not? Okay. If it doesn't span the entire vector space, it will be only spanning a subspace. All right. So we cannot tell that. But suppose it does. Suppose it can span the entire set, then you will say that the set of eigenfunctions is complete. All right. So let me just give this to you with an example. Okay, I will go and I will write it out in the iScribe. Can everybody see this? Okay. Uh, is this visible to everybody?
Yes,
Yes,
ma'am.
ma'am.
Okay, good. So for instance, let's imagine, okay, what did I tell you? I said I, J, and K. Okay. We know this spans three-dimensional space. Correct? Yeah, we know this. So similarly, you have A, you have eigenfunctions of A, the set of eigenfunctions, and we can ask the question, does this span the entire vector space? And per se, I don't know. Okay. Per se, I really don't know whether it does or not. Now, the point is, if it does not span the entire vector space, it will span, as I told you, a subspace. So, for instance, you know that if I took I and J only, I did not take I, J, and K, then this will span the XY plane, correct? It will give you every possible position on the XY plane. And this XY plane is a part, it belongs to 3D space. We know that, right? So it is a subspace. It is a subspace. So similarly, we can ask the question that yes, I have this Hermitian operator. Yes, I know its eigenfunctions form an orthonormal space, orthonormal set. But does this span the entire vector space? We don't know. We do know that if it does span something, that will be a subspace. Okay, it will follow all the rules of the vector space, but it may be leaving out a whole bunch of a whole part of the vector space which it's not describing. All right. So now the question is that those Hermitian operators which have a set of eigenfunctions which span the entire vector space, we give them a special name. We call them observables. Okay. So this is what I think I've written over there. Let me just get back. So let me write down this term once before we move on to my, so we call them observables. Okay. And what is an observable? Essentially, it's a Hermitian operator. Okay, it's a Hermitian operator. It has a set of eigenfunctions ui, and these span the entire vector space. Okay, so this is what we should remember, what an observable is. All right, so let me just get back to my slide. I'll stop this share. I will start the new share. Okay, so is the slide visible? Can everybody see this?
Yes, ma'am.
Yes, ma'am.
Yeah. So we should remember two terms from here. If the orthonormal set spans the entire vector space, we said that the set is complete. Okay, that is one term. And the other is that the Hermitian operator whose set of eigenfunctions form the complete set are called observables. So moment now somebody tells you that, hey, this operator is an observable, what all should you immediately think about? You should remember that the operator is linear. Please remember what is the definition of a linear operator. You should immediately remember that it is Hermitian, right? Remember the definition of a Hermitian operator. Next, All its eigenvalues are real, so they can be used as measurements. Their eigenfunctions form an orthonormal set. Yes. Not only that, the eigenfunctions form a complete set. So this complete is something new which I have thrown at you today. And what does it mean? You take a linear combination, you take any wave function belonging to the vector space. Okay. Remember how we are defining this vector space? So you pick up any wave function which belongs to the vector space and you can write it as a linear combination of these eigenfunctions. Not only that, this expansion is unique. Okay, this expansion is unique. And this is exactly what the next postulate speaks about. So I've just put this here because we are going to be starting, we're going to talk about this, and I've actually explained it to you. What does postulate 6 really tell you? It tells you a wave function representing any, sorry about that, a wave function representing any dynamical state of the system can be expressed as a linear combination of the eigenfunctions of A, where A is the operator associated with a dynamic variable, or in other words, it's an observable. Okay, so you have an observable, it has eigenfunctions. Any wave function which represents the dynamical state of the system can be expressed as a linear combination of those eigenfunctions. So I'm going to stop the share here and I'm going to ask you whether you have any doubts so far. Has everybody understood what postulate 6 is about? Sorry? Everybody is good? If you have not understood, please ask, okay? Because as I say, I should not assume that you have understood things and then just move on when the truth is otherwise. Is it okay?
Ma'am,
Yeah, please.
please explain once more, ma'am.
What do you want explained? So just give me a little bit of a clue. Okay. So which part did you not understand?
Postulate 6 only, ma'am.
Postulate 6 only. Okay.
Postulate 6 only.
Yeah, I will do that. I will do that. Just give me a minute. I will just find out where I have written postulate 6 in my notes. I will explain it on the iScribe. I think you find it a bit easier. It's also easier for me to do things when I write. I can never do things without writing. So I find it very difficult on an online class, but this new device has really saved my life. Okay. So I will just share it with you. Okay. All right. So I'm going to now change page. Yeah. Last time I forgot to do that. Okay. So everybody can see a blank page, right?
Yes, ma'am.
Yeah, otherwise I'll be scrolling on top of the old things like I did last time, right? I should not do that. Yeah. So what does postulate 6 talk about? Okay. It's exactly what I told you earlier. All right. Which is that you have an operator A. Now this is a special operator. It is what we call as an observable, right? Now, when I say that A is an observable, what all do I mean? I already said it to you, but I'll say it to you again. It obviously means that this is a linear operator. What does a linear operator mean? That if you have A operating on C1 psi 1 plus C2 psi 2 plus something like Cn psi n, right? What will you get? You will get some C1 A psi 1 plus C2 A psi 2 plus dot 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 Cn A psi n. Okay. Okay, somebody has just entered this thing. Let me admit this person. So this is what we mean by linear. What else do we mean? We mean it is Hermitian. Okay. What do I mean by Hermitian? That if I tried to do this, some phi A psi, this would also be equal to A phi psi. Right? What does this mean? It means that in terms of integration, I will write it out for you. Yes, I hope everybody has understood so far. Moment the operator is Hermitian, what do we know? We know its eigenvalues are real. We have proved this, okay? So please remember the proof. We also know its eigenfunctions form an orthonormal set. Okay. Now, lastly, we have called it an observable. So there is an extra meaning to this whole thing, and that is that the eigenfunctions form a complete set. Okay. So what do I mean by this complete set? Okay, so now I'm going to try and define this for you. What does complete set mean? All right. So basically, let's imagine you have a physical system. Right? You think about every configuration of this, okay? Every possible configuration of this, okay? They are defined by some functions, okay? Which are, the correct term to use would be wave functions, correct? So these wave functions, this all set of configurations, okay? I'm not writing the full thing, I'm just calling all set of configurations. These form an ensemble, right? And the whole set of wave functions which describe this ensemble, all right, I'm calling as the vector space. So anybody has any doubts about it? Let me explain once again. You have a physical system. All possible configurations of this forms an ensemble. Each of these configurations is described by some wave function. All the set of wave functions together form a vector space. Any doubt in this? Has everybody understood this?
Yes, ma'am.
Okay.
Yes, ma'am.
Now, you take some wave function that belongs to this vector space. Okay. You imagine that you have this particular wave function, this particular operator, this particular operator, which, okay, has set of eigenfunctions. Let's call it psi I. I know I used ui earlier, but I'm just calling it psi I right now. We may be able to write this psi as equal to some ci psi I. Okay, so remember this is like a capital psi. Okay, this is like a capital psi is equal to, this is a curvy psi. Okay, so they are different. This and this are different. Okay, so these are eigenfunctions. This is a wave function. Now, if I can do this for every psi belonging to F. Okay, so I'm calling this vector space F. Okay, if I can do it for every psi belonging to F, then A is an observable and the set of psi I is complete. Has everybody understood this? Has everybody understood this?
Yes,
Yes,
ma'am.
ma'am.
So now let us look at postulate 6 once again. Okay, so I'm just going to go back and look at postulate 6. So I'm going to stop this share. I'm going to, excuse me. All right, where did I go? Okay, unfortunately, I've gone off somewhere else. Resume slideshow. Yeah. So now just let's have a look at this. What do I mean by dynamical state of the system? I mean this capital psi that I talked about. All right. So let me So this dynamical state of the system is one psi, that capital psi, which I picked out of the vector space. And what we are saying is that this can be written as a linear combination of eigenfunctions of A, where A is an observable. Is this clear now? Have I
Yes,
managed
ma'am.
to clear your doubt? Yeah. So what are
Yes,
you
yes,
doing?
ma'am.
You have a physical system. You have all possible configurations of the physical system which form an ensemble. Each and every function that defines members of that ensemble forms a vector space. If you pick up one particular function from that vector space, so that is representing some dynamical state of the system, correct? You should be able to write it as a linear combination of the eigenfunctions of an observable. That is all what postulate 6 is telling you. Is this clear? Any doubts? Any further doubts? Because I can explain it again, no problems. Has everybody understood?
Yes,
Yes,
ma'am.
Yes,
ma'am.
ma'am.
Okay, good. So let's just move on now, all right? I need a small drink of water. All right. So now comes a very interesting idea, all right? We know that we can write down this expansion, as I told you, is unique, right? So you can write down this wave function as equal to some summation of ci psi I, correct? Yeah. So I think I had kind of explained this last time, but I will explain it again. Right. So let me just go to the iScribe. Okay. So I'm going to now change pages again. I will try and do it both on the real one as well as on the, uh, you know, the virtual one. So, okay, I've changed space. Everybody can see a blank sheet, right? Because I don't want to start writing on it again. So let us now, everybody can see a blank sheet, right?
Yes, ma'am.
Yes,
Okay,
ma'am.
good. So now let us imagine that we are thinking about a position in, three-dimensional space. So suppose I write for you 2, 3, 1. Okay, what have I written? 2, 3, 1, right? So now let's imagine that we draw up three-dimensional space like this. So this is your x-axis, this is your y-axis, this is your z-axis. And I say, hey, mark out this position, this 3, 1, 3, 1. Okay, mark it out. So what will you do? You'll say, okay, this is 1, 2, 3, 4. So this is 1, 2, 3, 4. This is 0, of course. Then here also there is a 1, 2, 3. And then along the z also there's a 1, 2, 3. And what will we say? We will say, oh, this is the x coordinate, right? So we'll go along this for 1, correct? Yeah, till here. And then we move along this till 3, correct? And then here also we'll have to go to 1. So the position is somewhere here, okay? Yeah, so this is 3, this is 1, this is also 1. Okay, I don't know, I should have drawn it a bit bigger, but I hope you understood. So now in our minds, okay, for all of us, there is no confusion about 1 being the x-axis, 3 being the coordinate along the y-axis, and again 1 being the coordinate along the z-axis. So in our heads, the unit vectors I, j, and k are very strictly ordered. Okay. In general, we wouldn't write k first, then j, then I, right? We wouldn't do that. We have the strict order in our head. And because we have that strict order in our head, when I give 1, 3, 1 to you, to me, to, somebody who's sitting in Majestic, somebody who's sitting in Delhi, somebody who's sitting in New York, okay, we will all find the same position, correct? So thereby, let's imagine that you can do the same thing for your wave functions, okay? So let's try and do the same thing for your wave functions. So what do we do? Essentially, we try and write the suppose we make a strict ordering. Okay, so we know that this is your A. Remember, this A is a special A now. This is an observable. Correct? This is an observable. It has a set of eigenfunctions ui, which are a complete set, right? And we know that we can pick up this wave function, okay, which belongs to this vector space, and we can write down this psi as summation over I ci ui. Okay. Now imagine that these ui's are very strictly ordered, which means that we have, or yeah, u1 first, then u2, then u3, then un. Just like here we had the I first, the j first, the I first, the j first, and the k third. Yeah. Like that, we have u1, u2, u1, u2, u3, like that till un, strict order. Okay. Nobody messes with it. Then what can we do? We can just like, we could refer to this position here, this position over here, just with these coordinates. Similarly, we could refer to this wave function here, this psi, okay, in terms of just the CIs, the set of CIs. More correctly, what we do is we write a column vector, all right, with C1, C2, C3, all the way to Cn. Okay. Then what happens is that we don't need to really think about the mathematical function. See, this is a mathematical function, correct? But here, what are we doing? We are writing it as a column matrix. Okay. So has everybody understood this idea? Let's just discuss this a little, okay? Because this is very important to understand. What was the psi originally? Okay, let me just try and get my annotate button. What was the psi originally? It was a mathematical function, right? It was a complex mathematical function. But what is it over here? It is a column matrix. What are each of these numbers? The C1, C2, C3, they are numbers. They are complex numbers, but they are numbers. So just a column of these matrices, of these numbers, represents, it has the same representation as this mathematical function. Has everybody understood this? This is a very, very important thing, because this is the base of your matrix mechanics. Yes, Akshaya, please tell me.
Can you repeat this, ma'am?
Yeah, I will repeat it. So have you actually understood this example I gave of the position? The
Yes,
three-dimensional
ma'am.
position? You've understood it?
Yes,
Okay.
yes, ma'am.
So you know that 1, 3, 1, which I put, whether you mark that position, I mark that position, whether somebody, as I said, in Mangalore, puts that position, or somebody in Chennai does it, we know we will mark exactly the same position. You agree with me?
Yes, ma'am.
Yeah.
Yes, ma'am.
You agree with me, right? Now the
Ma'am.
point is that suppose now, what have we discussed so far? That this A is an observable. It has some eigenfunctions. Suppose now these eigenfunctions, so like in three-dimensional space, what did I do? I will always put I first. I will always put J second. I will always put K third. Correct? Strictly we know that order in our heads, right? Similarly, let's imagine that we put always this first eigenfunction of A, we will take one eigenfunction and we'll put it. That's this U1. That is always first. Then it is U2. Then it is U3. Okay? Like that till UN. Strict order. We also know that when we pick up any wave function from the vector space. So what did I call it over here? I called it this psi. We can write it like this. Why can we write it like that? Because this A over here is an observable, and we know the set of UIs form a complete set, correct? So we can write this psi as equal to summation over I Ci Ui. Now instead of writing it like this complicated thing as a sum of some functions. Eigenfunctions are also functions, right? So C1 multiplied by this function called U1 plus C2 multiplied by this function called U2 plus C3 multiplied by this function called U3. Instead of doing that, I have this U1, U2, U3, U4 very strictly in my mind. Okay. All right. The order is correct. Then I can forget about all these UIs. I can only bother with the CIs. Okay. So moment I write it like this, I know this is actually C1 is multiplying U1 plus C2 is multiplying U2 plus C3 is multiplying U3 up to Cn multiplying Un. So I can just remember the C1, C2, C3 up to Cn instead of writing it in this complex way of some number multiplying these eigenfunctions U1, U2, U3 and so on and so forth. Have you understood so far?
Yes, ma'am.
Okay. So
Ma'am,
thereby what is happening now, you had on the left hand side a wave function, right? It's a function. It describes some dynamical state of the system. That was a function. Now what have you done? You have managed to change it into a column matrix. Column matrix of some numbers, you C1, C2, C3 up to Cn. Remember, there is a mathematical function also which is there. Okay? Because we know that C1 will multiply U1. U1 is a mathematical function. It is also an eigenfunction of this observable A. But we are right now not bothering with that. Okay? We will know that if we write it like this, C1, C2, C3 up to Cn, we will have just these numbers. And if we remember this, it is enough. So is this clear?
How is this dimensionally okay, ma'am? Isn't psi a complex mathematical wave function?
Correct.
And how is representing it as a scalar matrix dimensionally okay, ma'am?
So the point is that please remember, yeah. So that's a very interesting question. What is this C1, C2? When I write it like this, okay, so let me just go back here. When I write it like this C1, C2, Cn, okay, this is my, I'm saying this is my psi now, new representation of the psi. What do I actually mean? The actual meaning is that this psi is equal to C1 into U1 plus C2 into U2 plus Cn into Un. This U1, U2, Un will have the same dimension as psi. Okay? What I'm doing is that I'm just remembering these numbers. So remember, it's like your, what had we done on the top? So let me just remove this. I'm trying to let you remember this particular thing. 131 we wrote, right? You can ask that, hey ma'am, I want a vector, right? How is 131 a vector? That is because the vectorial behavior of it is coming from 1 into I plus 3 into j plus 1 into k. So this I, j and k are vectors, just like this is a position vector. Okay, so this is a vector. These three, your I, your j, your k are also vectors. Similarly, come to the bottom over here. Your psi is a wave function. Your u1, your u2, your un is also, they are also wave functions. So dimensionally, there's no problem. You're only remembering this psi in terms of your C1, C2, Cn. Just like you are looking at this position vector, go to the top of the page, I'm talking there as 1, 3, 1. Okay, the vectorial aspect is hidden in that I, j, k. Is this clear now?
Yes, ma'am.
You've got it?
Yes, ma'am.
Any other doubts, please? But it does seem a bit shocking, but we have already experienced it. We write a set of 3 scalar numbers and we say, hey, this is a vector, correct? And we all accept it, isn't it? Similarly, here, that's what I'm saying, that let me just annotate again. we have this set of scalar numbers which is forming a column matrix, and it represents this mathematical function which is a wave function. Is this clear? Are you a little more comfortable with it now?
Yes, ma'am.
Okay. Any other doubts, please? Because this was a very important question, I think. Any other doubts? Okay, so what's the time? I should look at it. I shouldn't just run away. Okay, we are almost at the edge of time. All right. Now, let's take it a bit further. Okay. We are able to write these wave functions as, so I hope everybody is happy right now. Okay. I mean, or at least you've at least got this idea that I can write this wave function as a column matrix. Okay. I hope everybody has done. So let us now take the idea of what shall I say? Let's consider the scalar product. Okay. Let's consider the scalar product. Scalar product, what do I mean? I also call it the inner product, right? Yes, I'm going to go back to my iScribe and I will change pages because otherwise you will see a whole bunch of nonsense then. Okay, so I'm going to change the page. Okay, so we know that this wave function can be written excuse me. So we know it can be written as a column of numbers, correct? Column of scalar numbers. Now, one thing that you have to remember over here, that this C1, C2, Cn, they depend upon which set of eigenfunctions I'm using, right? If I'm using eigenfunctions of A, then it is C1, C2, Cn, right? Suppose I decided to use another observable, say an observable B, okay, which had a set of eigenfunctions Vi, all right, then obviously the same psi, I could write it as some, okay, say, uh, so instead of this, I could write it as B1, B2, all the way till Bn, correct? So how I'm writing the psi depends upon which basis set I'm using or which complete set of eigenfunctions I'm using. If I change the observable, I will get a different set of eigenfunctions and thereby my representation becomes different. Is this clear to everybody? How do I explain it? For instance, you know, three-dimensional space, I can write a position in terms of I, j, and k, so x, y, and z, or I can write it in spherical polar coordinates, r, theta, phi, or I can write it in cylindrical coordinates, r, theta, h, right? And we can all get the same position. But the numbers which qualify it are going to be different. What I write for I, j, k, x, y, z will not be the same as what I will write for r, theta, and phi. But they can represent the same point. Correct? Does everybody understand this? Similarly, the same wave function can have different representations depending on whether you're taking this observable or you're taking this observable. Is this clear? Any doubts?
No, ma'am.
Okay, good. So that is one problem of writing it as this column matrix. Okay, you realize that because the column matrix, we will have to write it as an expansion of in terms of some eigenfunctions. Okay, and depending on which operator I pick, whose eigenfunctions I'm going to use, I'm going to have different looking representations. One thing you have to be sure of, that the number of these numbers, okay, the C1, C2, Cn, this number will not change. Just like we know for three-dimensional space, you have to have three independent vectors. So you will never be able to write it with a smaller number. So for instance, you can write it as x, y, z. You can write it as r, theta, phi. It's not that you once you went to spherical coordinates, you could reduce the number, right? Or you can write it as r theta h, again 3. So similarly, here also please remember this n will remain the same. Okay, no matter what representation. Now, here we will come to the concept of Dirac's, what is called as the bracket notation. Okay, and what we will say is that each of these form what we call as a ket vector. Okay, so we will write some number here. Let's try and put this psi itself. Okay, okay, so this is called a ket vector. All right, obviously this ket vector is in the representation using A. This is also a ket vector, but this will of course, so we can call it this, and this will be with B. Okay, but in general this represents a ket vector. Okay, so please remember the ket that we are talking about, it will depend upon which particular set of complete eigenfunctions you are using, which observable you are taking into account. All right, and you will be able to write these column matrices. From here, in the next session, which starts at 2, I will try and explain to you that in terms of if we start writing these wave functions as column matrices, what happens to the inner products? What happens to the form of the operators? Okay, so we will handle that in the next class. Okay, so I've already eaten into your bit of your charging time. All right, so okay then, and in the next class I will not start off with a recap, but if you have any doubts with regards to what I taught you just now, please tell me. We will stop, we will re-examine all those things, clear all your doubts, and then we will move on. Okay, so I will stop the share. Any doubts right now you want to ask me? You can go ahead and ask. Any doubts, please? Okay, I will assume there are no more doubts. All right, we will just move on after this, and we will meet each other at 2 o'clock. Okay, I will send you another invite. Okay then, so I see people are putting in their roll numbers. I will wait. You can start leaving once you put in your roll numbers, and I will stop the meeting only after I'm sure that everybody has put in their roll numbers. Okay, so as in how you put things in the chat, you can just leave. I'll stop the recording right now.